Hello everyone, this is Dr. Vishal Trivedi from Department of Biosciences and Bioengineering, IIT Guwahati. And in our previous lecture, what we were discussing about the basics of the separation techniques, and as well as then we started discussing about the different aspects related to the chromatography. And in that context, we have also discussed about the protein purification system, and then we have shown you a small demo how to operate a typical chromatography system and what are the different steps or the precaution you have to take. And following that discussion, today we are going to discuss about the different chromatography techniques. So, why and how we can exploit the different chromatography techniques, because the protein what we are going to purify, or what we are actually going to purify in this course is having the different properties. So, let us see what are the different properties a typical protein molecule will have. So, if you see that the protein molecule, so protein molecule is normally being synthesized as a linear chain of amino acids, and as soon as the protein is synthesized or a small polypeptide is being synthesized from the ribosome, it starts going through a process of folding. This folding is always being governed by the intramolecular interaction between the side chains which are present on the amino acids, and as well as there are additional forces which are actually playing crucial role in folding a protein into a proper 3-dimensional conformations. And once the protein is being folded properly into a 3-dimensional conformations, what you will see is that it is going to arrange all the amino acids in such a way, so that it is going to have the many different types of properties which can be exploited in different types of chromatography techniques. So, let us see what are these techniques, what are these properties. So, the protein which is going to be folded properly is going to secure its hydrophobic surfaces or hydrophobic amino acid groups inside the core, whereas it is actually going to keep charge on the surfaces. So, you have the two properties, one is the charge which you can exploit, and then you can also exploit the presence of these hydrophobic patches. Apart from that, the protein is also maintaining a 3-dimensional conformations, and these 3-dimensional conformations, 3-dimensional arrangement of the amino acid is also forming a small ball like structures, and these ball like structures have a definite surface area which is actually corresponding to the length of amino acid or indirectly to the molecular weight of the amino acid. So, that surface area is also can be a property which can be exploited in a chromatography techniques. Apart from that, the amino acids which are being arranged in the protein structures are also providing the specific 3-dimensional conformations, and these specific 3-dimensional conformations are being utilized in the is providing the affinity or the biological affinity to the cognate receptors or the ligands, and that can be also exploited in a affinity chromatography. So, let us see what are the different chromatography techniques you can use to exploit these properties. So, as I said, you have the hydrophobic core. That hydrophobic core can be exploited in a technique called as the hydrophobic interaction chromatography. Similarly, you have the affinity parameters or the affinity regions on the proteins, and that can be exploited in a affinity chromatography. Then you have the surface area as a property, and that surface area as a property can be exploited in a gel filtration chromatography. And lastly, you have the charges, different types of charges present on the protein, either the positive charge or the negative charge, and that can be exploited in a ion exchange chromatography. So, today we are going to discuss about the ion exchange chromatography. So, what is the basic principle of the ion exchange chromatography? This chromatography distributes the analytes, which means the proteins. So, different types of proteins as per the charge and their affinity towards the positively charged matrix, the analytes bound to the matrix are exchanged with a competitive counter ion to elute. The interaction between the matrix and the analyte is determined by the net charge, ionic strength and the pH of the buffer, which means this particular ion exchange chromatography is actually going to exploit the intrinsic charge, whether it is positive or the negative present on the protein, and its interaction with the oppositively charged charges present on the matrix. So, in a process what happen is, if a positively charged protein is there, it actually going to replace the counter ions, and then counter ions are and the protein is going to bound, and this binding is going to be affected by many parameters such as the pH of the buffer, the ionic strength and all other parameters. So, let us see, if you take a example, let us see what we have is, we have a positively charged matrix. Okay. So, if you flow a mixture of the positively charged analytes, for example, you have the 4 analytes, one is called M0, M minus 1, M plus 1 and M2 minus. So, what you have is, you have the 4 analytes and you are flowing them onto a positively charged matrix, which means this positively charged matrix is going to have the affinity for a negatively charged group. So, as soon as you flow these 4 molecules, so you can see that you have the M2 minus, M minus and M0. So, M0 means the protein which does not have the charge, it is a neutral protein. M plus means it is a protein which has the basic charges, and then M minus 1 or M2 minus is having the negative charges. So, in this process what will happen is, once you flow these complex mixture, the M2 minus as well as the M minus is going to bind the matrix, whereas the M plus, which is actually going to repel the bound charges, and M0 does not have any charge. So, it will also not going to bind the matrix. Now, ultimately what you can do is, you can flow the negatively charged ions, and that actually is going to displace these M minus or M2 minus, and ultimately you are going to see the separation of the 4 different types of proteins. One, the 2 proteins are not going to bind to the matrix, whereas the other 2 proteins which are binding to the matrix is having the differential affinity, because this particular protein has the minus 2 charge, whereas this particular protein has the minus 1 charge. So, the when you going to elute with the help of the negatively charged counter ions, this M minus 1 is going to be elute first. So, this one is going to be elute first, whereas this one is going to be elute later on, because both of these have the differential charges and they will going to have the differential affinity to the matrix. Now, what are the different types of matrix which are available for performing the ion exchange chromatography? The matrix used in ion exchange chromatography is present in the ionized forms with the reversibly bound ion to the matrix, which means if you have a matrix, it is actually having the positive or the negative charge. So, it is going to have a positive charge, and then it is going to have the counter ion, which is a negative ion. The ions present on the matrix participate in the reversible exchange process with the analyte. Hence, there are 2 different types of ion exchange chromatography. One is called as the cation exchange chromatography, the other one is called as the anion exchange chromatography. As the name suggests, the cation exchange chromatography is the chromatography where matrix has a negatively charged functional group with a affinity towards the positively charged molecule, which means the cation exchange chromatography, the matrix is going to be connected to a negatively charged group, and then it is going to have the bound positively charged counter ions. The positively charged analyte replaces the reversibly bound cation on the and binds to the matrix, which means when you flow the positively charged proteins, it is actually going to displace the reversibly bound ions, which means the cation in this case, and it will bind, and then ultimately what you are going to do, you are going to flow a strong cation such as the Na plus in the mobile phase, and as a result what will happen, the matrix bound positively charged analyte, which is the protein, is going to be displaced, and that is how the analyte is going to be eluted. Now, in the anion exchange chromatography, it is actually going to be completely reverse. So, in the anion exchange chromatography, the matrix has a positively charged functional group, which means the matrix is going to be connected to a positively charged functional group, which is actually having a counter ion of negatively charged anions. So, it has affinity towards the negatively charged molecules. The negatively charged analyte replaces the reversibly bound anion and bounds to the matrix. In the presence of a strong anion, for example, the chloride, in the mobile phase, the matrix bound negatively charged analyte is going to replace, and that is how the analyte is going to be eluted from the matrix. There are different types of the cation or the anion chromatography columns or the matrix what you can use. These are actually either the weak matrix or the strong matrix. The weakness or the strongness of a matrix depends on the type of functional group or type of ionizable group present on the matrix, and that is how they are being classified either as the strong cation exchangers or the weak cation exchangers. So, let us see what are these molecules. So, in the strong cation exchangers, you have a functional group which is called as the sulfonic acid or the SP. The pH range where you can work with this particular type of cation exchanger is 4 to 13. The examples are the SP Sapphoros, SP Sephardex, and all these. Similarly, you have the weak cations. Weak cation is containing the carboxylic acid as the functional group which is present onto the matrix. The pH range in which you can use this is 6 to 10. The examples are the CM cellulose, CM Sapphoros or CM Sephardex, and all these other kind of the column matrix which are being available from the different types of vendors. Similarly, you have the strong anion or the weak anions. Within the strong anion, you have the quaternary amine, which is actually going to have the positive charge, and the range in which you can use this particular matrix is in the range of 2 to 12, and the examples are Q Sapphoros, Dow X, and all that. Similarly, you have the weak anions where you can have the primary amine or the secondary amine or the tertiary amines. One of the classical example is the DAE, and the range in which you can use this particular matrix is 2 to 9, and the examples are DAE Sapphoros and DAE cellulose and all other matrices which are available from the different vendors. But the question comes, how you are going to select the matrix, how you are going to perform the ion exchange chromatography. So, let us discuss that. So, this is the basic principle through which the cation or the anion exchange chromatography is working. So, you can see that you have the cation exchange chromatography or the anion exchange chromatography where you have the bead bound matrix. So, in this case you have a negatively charged group which is attached to the sodium, and the counter ion sodium is attached. Now, once you flow the positively charged proteins, this positively charged protein is going to compete for the counter ion, which means sodium, and in this process what will happen is the sodium is going to be displaced from the matrix and the positively charged protein is going to bound to the matrix. Now, once you flow the sodium back, which means if you flow very high concentration of the counter ion sodium, the sodium is again going to bind to the matrix and it is going to elute the proteins. Similarly, in the anion exchange chromatography, you have the matrix where you have the positively charged ions and then you have the counter ions. Once you add the negatively charged protein, it is actually going to go through with the exchange process. In that process, the chloride is going to be displaced from the matrix and the protein is negatively charged protein is going to bind, and then once you flow very high concentration of the counter ions, the protein is going to be displaced from the matrix and it is going to be eluted, and your matrix is again going to have the counter ion bound and it is going to be ready to use. Now, with this brief discussion about the cation or the anion exchange chromatography, when you start a ion exchange chromatography, the first question comes at which matrix I should use and at what pH and under what conditions and how to perform the ion exchange chromatography. So, let us discuss that. If you would like to run the ion exchange chromatography, you have to consider the three different parameters. One is you have to select the appropriate matrix. Once you select the appropriate matrix, then you have to prepare the matrix for the chromatography, and then ultimately you are going to perform the chromatography by the following a set protocols. So, let us discuss first how you are going to select the matrix. Now, selection of the matrix is a very crucial parameter or crucial process if you would like to perform the ion exchange chromatography, and the matrix is going to be selected based on whether the analyte is going to have the negative charge or whether it is going to have the positive charge. Now, you know that the protein has the different types of charges, whether it is the positively charged or the negative charge, or some are the polar amino acids or the non-polar amino acids. So, if you take the protein to different pH, the ionization of these side chains is always been changing, and as a result the effective charge on the protein is always vary as you go from one pH to another pH, and because of that it is important to calculate or it is important to know whether the protein has the positive charge or the negative charge. One of the parameter which actually is going to decide whether the protein is going to have the positive charge or the negative charge is the isoelectric point. So, the first thing what you have to know if you would like to purify or select the matrix is what will be the isoelectric point of the protein and what will be the net charge on a particular pH, because then only you will be able to decide whether my protein is going to have the positive charge or the negative charge. The second thing is, once you selected the pH, you also have to decide whether this particular pH is not going to affect the structural stability, because the ultimate goal of any chromatography technique is to purify a protein which is three dimensionally stable, which should have its native conformations as long as possible or as much as possible, because the ultimate goal of the chromatography technique is to purify the functionally active three dimensionally native proteins. So, you have once you selected the pH or once you decided that okay, at this particular pH the protein will going to have the positive charge, I can use the particular ion exchange matrix, but then you also have to consider whether the protein is structurally stable or not, because if the protein is not structurally stable, it is actually not going to give you the native protein, then your protein is going to be denatured, and the purification of a denatured protein is not very desirable. Now, once you decided that protein is having the structural stability, it is also maintaining the native conformation. The third parameter what you have to also see is if this protein is an enzyme, whether the enzyme is also retaining the activity, because you are going to perform the chromatography techniques for two applications. One, you would like to isolate a structural proteins, or you would like to isolate the protein in a native conformations, and then you use them for the downstream applications or downstream processes. That could be that you can use these proteins as a vaccine, or that you can use this protein for generating the antibodies. But sometime you also isolate these proteins simply by performing the enzymatic reactions, either these enzymatic reactions for the industrial applications or simply by doing some basic research. So, that is also very important, that you also should ensure that at this particular pH, your protein is also having the retaining the enzymatic activity. Once you done with this, and all these parameter is linked to the isoelectric point, because that is the thing which is actually going to determine what will be the net charge at that at a particular pH. And you can see how the PI is going to decide the net charge. The information of a isoelectric point will allow you to calculate the net charge at a particular pH on a protein. A cation exchange chromatography can be used below the PI, whereas an anion exchange chromatography can be used above the PI value, which means at the PI value the protein is going to have the net charge 0. So, if you go below to the protein PI charge, you are going to generate net positive charges onto the protein, and that is how you can be able to use the cation exchange chromatography. Similarly, if you go to the above to the PI values, you are going to have the negative charges, and that is how you can be able to use the anion exchange chromatography. Let us take an example. For example, if you have the PI value of 7.4. Now, if I have to use, and I have determined that the protein is having the no issue with the stability as well as the enzymatic activity, then I can use the cation exchange chromatography at the pH 5.4, or I can use the anion exchange chromatography at a pH of 9.4. Now, whether I will use the cation exchange chromatography or the anion exchange chromatography, it will depend whether the enzyme or the protein what we are planning to purify utilizing the ion exchange chromatography is having the native conformation at this pH as well as maintaining the enzymatic activity. If it is not maintaining the enzymatic activity or the 3-dimensional conformation at this pH, then we have to then we cannot perform the cation exchange chromatography. Instead, we have to use the anion exchange chromatography, and we also have to decide whether at that particular pH also it is maintaining the stability 3-dimensional conformation as well as the enzymatic activity. So, now the question is how you can be able to determine the PI of a particular protein or the isoelectric point of the protein. There are multiple ways in which by which you can be able to calculate the isoelectric point of a protein. One is you can be able to use the theoretical calculations, which means if the amino acid sequence of a protein is known, then what you can do is you can take the individual amino acid and their pK values will be used to calculate the pH at which the net charge will be 0. So, what I am saying is the net charge, not the total charge actually. So, means at the isoelectric point, the number of positive charges and the number of negative charges are going to be equal, and that is how the net charge on the protein is going to be 0. So, by theoretical calculations, one of the primary requirement is that you should know the amino acid sequences. So, if you know the amino acid sequence, you can be able to use the theoretical calculations, or you can use some of the web servers. For example, I have given you a link so that you can actually go and put some amino acid sequences and know what will be the isoelectric point of that particular protein. So, once you go to this particular link, what you have to do is you just copy paste your amino acid sequence into this box, and then you ask the software or the web source to calculate the pi values. It is not going to do anything else except it is actually going to take all the amino acids, it will take up all their pK values, and then it was just going to give you the average number at average pH at which the protein is going to have the 0 charge or the net 0 charge. Now, if you do not know the amino acid sequence and still you would like to calculate or want to calculate the isoelectric point, then you can use the experimental calculation, which means you are going to perform the experiments with the purified protein and you can calculate the isoelectric point. Let us see how we can calculate the isoelectric point using the experimental conditions. So, for the experimental protein conditions, the basic principle is that the protein is going to have the minimum solubility in a solution with the pH that corresponds to their pi and often precipitate out of the solutions. So, when the protein is going to precipitate, it is actually going to start going to form the particles, which means it starts going to produce the particles. So, the protein is when you will reach to the pi value, it is actually going to start showing the insoluble particles, and these small particles are going to show you the scattering of the light. So, you can actually use this particular type of behavior of a protein in the aqueous solutions with different pH. So, what you are supposed to do is you take the append-offs of the different pH. For example, you take the pH 3, 4, 5, 6, 7, 8, 9 and 10, and then what you do is you incubate the equal amount of the proteins and you measure the scattering of this particular solution at the 660 nanometer in a spectrophotometers. And when you plot this, what you will find is that the protein is following a biphasic behavior where the solubility is going down and then solubility is going up. So, what will happen is as you are going from the pH 2 to pH 5, the protein is actually the charges present on the protein is getting neutralized, and as a result you are actually having the minimum solubility, which means the maximum scattering. So, once it reaches to the minimum solubility, then after that if you increase the pH again, it is actually again regaining the charges and it is again becoming the soluble into the solutions, which means if you plot the protein's pattern along the different pH and if you plot the scattering versus different pH, and if you consider the maximum scattering as the 0 solubility and the minimum scattering as the 100% solubility, and so the protein at the place at which the protein is going to give you the maximum scattering or the 0 solubility, that is the place where which is actually is going to be considered as the isoelectric point. So, if you follow this particular type of pattern, the isoelectric point is somewhere between the 5 to 6. But if you narrow down these pH conditions, you can be able to determine the pi value of the particular protein very precisely. Now, once you calculated the pi values, you also have to consider the structural stability as well as the enzymatic activity that we have already discussed. Now, once you have decided whether you would like to use the cation exchange chromatography or the anion exchange chromatography, you have to process these matrix for utilizing it into the ion exchange chromatography columns. Now, in nowadays most of the chromatography matrices, whether it is the for the anion exchange chromatography or the cation exchange chromatography, is always coming free of the any pre-processing. For example, it does not require any pre-processing, it is always been coming in a ready to use mode, but in case some of these matrices are not present in the ready to go mode, then you might have to process them to make them for the useful matter. Okay. So, what you are supposed to do, you have to do three activities. One, you have to do the swelling of the medium, then you have to remove the very small particles which are actually going to affect the many parameters, and then you have to equilibrate the matrix with the counter ions, so that it will actually participate in the exchange process. Swelling of the process, swelling makes the functional group to be exposed for ion exchange. So, swelling of the medium means where you are actually going to swell the matrix, so that it is actually going to take up the water from the media, and then it is actually going to expose its functional group for participating into the ion exchange process. The swelling protocol or the swelling process is different, whether it is the anion exchange chromatography or the cation exchange chromatography. For the anion exchange chromatography is usually been carried out by treating it with a very mild acid, for example, the 0.5 normal HCl, and then with a 0.5 normal NaOH. So, with this treatment, the functional group which are present on the medium is going to be exposed, and they are ready for the exchange process. Exactly the reverse is going to do with the cation exchangers. The matrix can be treated with the EDTA for removing the impurities or the small metals. So, because the metals are the cations, so you also have to ensure that there is no metal is present in the process. Then the next step is removal of the very small particles. This fine particle will decrease the flow rate, and it will actually going to participate into unsatisfactory reaction, which means sometimes this small particle itself is going to compete with the proteins, and as a result it will actually going to interfere into the binding process. Also, because there are fine impurities or fine particles, they are actually going to decrease the flow rate. So, and both of these processes are going to make the chromatography process very difficult. So, to remove the fine particles, the exchange is repeatedly suspended in a large volume of water, and after the larger polymers have been settled down, the slowing sedimentation rate decanted, which means what you do is you take the matrix into a beaker, okay, and then you fill it with the large quantity of water. So, what will happen is, because these matrix are very heavy particles, they will settle down first, whereas the fine particles are going to be remain in the solutions. So, what you do is you decant these small particles and you repeat this 4 or 5 times, that actually is going to remove these fine particles from the matrix, and that is how your matrix is going to be more pure and more useful for further downstream applications. Then you have to equilibrate the matrix with the counter ions. This is important because it is because you have to ensure that the whether it is an anion exchange matrix or the cation exchange matrix, it should have the bound counter ions. You have to perform these processes like NaOH you have to do to provide the counter ion, which means when you treat the things with the NaOH, it is actually going to introduce the counter ion, the sodium, and so on. Once you produce the counter ions, or once you perform these processes, what will happen is the matrix which is actually containing the positively charged groups is going to bind the negatively charged counter ion, and now this matrix is ready to be used into the ion exchange chromatography process or the protocol. What are the buffers you can use? So, it is not that you can use any buffer of your choice, you have to use the buffer, considering that the buffer is going to maintain a stable pH and also it is not going to interfere with the chromatography techniques. So, these are the different buffers what you can use for cation exchange chromatography. You can use the citrate buffer, lactate buffer, acetate buffers. You can use the all other these type of buffers. What you have to consider is their pK values and as well as the working pH. So, depending on what pH you are interested, you can choose the particular type of buffer, because in this particular working pH only it is going to maintain a stable pH, so that it should not vary, because as soon as the pH is going to vary, it is actually going to change the charge present on the particular protein, and as a result it is actually going to affect the overall elution process. Because what you do not want is the elution should be done simply by varying the charge on your protein itself. What you want is that you can actually put the sodium or chloride as a competitive counter ions, so that it is actually going to follow the basic principle of the ion exchange chromatography. Similarly, you have the different types of buffer for the anion exchange chromatography. So, the only thing what you have to consider is what is the pH in a range in which you are interested to work. Now, let us see how to do the operation of the ion exchange chromatography. So, the first thing is you have to equilibrate the column with a suitable mobile phase. The pH of that mobile phase is going to be decided based on what is going to be the isoelectric point, and once you do that, the counter ion present on the buffer is going to bind to the functional group which is present onto the matrix, and as a result your now column is going to be ready. The column material, so in this process of the equilibration of the stationary phase, the column material should be chemically inert to avoid the destruction of the biological sample, which means the matrix should not react with the biological sample. It should allow the free flow of the liquid with minimum clogging. It should be capable of withstanding the back pressure and should not compress or expand during the operation. Now, you are going to load the proteins to the matrix. So, in this case we are loading the positively charged. So, the protein is having the positive or the neutral charge protein. So, what will happen is, and you have the negatively charged protein. So, if you have a mixture of the positive charges, positively charged proteins, negatively charged proteins or the neutral proteins, it is actually going to flow to the matrix, and as you can see, this matrix is having the positive charges. So, it is actually going to show the affinity only for the negatively charged proteins, and then that is how the protein is going to bind to the matrix or going to bind to the ion exchange matrix. Then what you have to do is you have to flow the samples, and the sample, the only thing what you have to do, the only precaution what you have to do is that the sample should be free of the suspended particles, which means it should not having suspended particle to clog the column, because that actually is going to reduce the flow rate, and then ultimately you are going to do the elutions. So, there are many ways to elute an analyte from the ion exchange chromatography columns. One is the stepwise gradient, and the number 2 is a continuous gradient either by the salt or the pH. So, there are two modes, either you do the stepwise gradient. The stepwise gradient means that you are going to, for example, if I am using the NaCl, so that actually is, I can use a linear gradient, which means I can use from 0 to 100 millimolar. So, in this case it is actually going to be a linear. For example, it is going to be 0 millimolar, 1 millimolar, 2 millimolar, like that. So, it is going to be a linear. Okay. The second is that if you want to use the stepwise gradient, then what I can do is I can take the 10 millimolar, elute something, then I take 20, then I take 30 and so on. So, then ultimately I take the 100 millimolar. So, that is called as the step gradient, whereas the continuous gradient means I will going to follow a process, so that it is actually going to maintain a continuous gradient, which means after every microliter what is going to be added into the system, some amount of the sodium is going to be added, and that is how it is actually going to maintain the linear gradient. The step gradient is does not require any type of machine or something, that can be done in a manual mode, whereas the linear gradient or the continuous gradient is require a gradient mixer. This gradient can be made of either the salt or the pH, which means you can make a linear gradient of pH, so that it is actually going to change the pH. As it is going to change the pH, it is actually going to change the charge onto the protein, and that is how it is actually going to come out. So, once you flow the salt, it is actually going to compete with the bound protein, and that is how the protein is going to come out. And as you remember, we have discussed, if the protein has the multiple charges, it is actually going to be more affinity, going to show more affinity. That is why it requires the more amount of salt or more amount of counter ions, and the protein which have a lesser amount of charges, it is going to follow the lesser sanket. Now, ultimately once you are done with the ion exchange chromatography, you have to do a next process, that is called as the column regeneration, which means you are actually going to regenerate the column, so that it is actually can be reused to the next chromatography technique. After the elution of the analyte, the ion exchange chromatography column requires a regeneration steps to use the next time. Column is washed with a salt solution with a ionic strength of 2 molar to remove the all non-specifically bound analyte, and also to make all functional group in a ionized form to bind the fresh analyte, which means what you are supposed to do is you are going to wash this with a 2 molar NaCl. What will happen? Once you wash it with the 2 molar NaCl, it is actually going to remove all the proteins, all the proteins, and as well as the other kind of the biological molecules, which is not desirable, but it is bound. For example, one of the thing which going to bind to the most of the ion exchange chromatography is DNA, because DNA is negatively charged. So, it will go and bind to these functional groups, but that is not what you want, and because these molecules will bind to the functional group, this functional group will not be no longer available. So, that is how you have to wash these columns with a very strong salt solution, so that all the biological molecules are going to be removed, and then these functional groups are free to bind the buffer ions. So, that now the column is ready for the next round of purifications. Now, let us see the applications of the ion exchange chromatography. So, one of the major application of ion, or the major application of the ion exchange chromatography is that it can be used to purify the water. So, water is having the different types of impurities. For example, it has the hardness, it has the alkalizations, it has the different types of contamination, for example, the fluoride or the heavy metal, and all these can be removed because the fluoride is the negatively charged, whereas the hardness is because of the different types of carbonates and other types of molecules, and heavy metal is always been because of the arsenic or other types of heavy metals. So, this is actually an ion which is being present as the impurity into the water, whereas the heavy metals are falling under the category of the cation, and all other things are. So, when you flow the water to the ion exchange matrix, whether it is the anion exchange matrix or to the cation exchange matrix, you can be able to purify or you can be able to remove these substances. Let us take an example how you can actually be able to remove the hardness or you can make the water more soft. So, the groundwater has a several metals such as calcium, magnesium and all other cationic metals. A cationic exchange matrix with the bound sodium is packed in the column. So, you take a column where you have used the cation exchange chromatography and this cation exchange chromatography is bound to the sodium. Now, what you do is you flow the hard water containing the calcium and magnesium, and once you flow them, the calcium as well as the magnesium is going to displace the sodium from the bound matrix, okay. And as a result the water, whatever the water will come out is actually going to be devoid of the calcium as well as the magnesium. Now, packed in the column and the hard water containing calcium magnesium is passed to the column. In this process, the calcium present in the solution preferentially migrates from the solution to the matrix, whereas sodium ion present on the matrix migrate into the solutions. So, this calcium and magnesium will remain trapped within the matrix, whereas the water will come out along with the sodium. Now, once you are keep using this cartridge, so this cartridge has the limited capacity, so that it can be able to bind the calcium and the magnesium, and afterwards what you can do is you can just flow the solution of the NaCl, and once you flow the solution of the NaCl, what will happen is all the calcium and magnesium which is being trapped from the water is going to be displaced from the matrix and it will come out, and that can be thrown into the suitable place, and then this cartridge is again be ready to use. So, this cartridge can be used on the several occasions, and that is how you can be able to remove the all type of the heavy metal as well as the all other transition metals, and that is how you can be able to remove the hardness from the water. So, this is just a simple application or simple description of how the cation or the anion exchange chromatography can be used to purify the water. Now, in our subsequent lecture, we are actually going to discuss about the research problems where you can be able to utilize the ion exchange chromatography and how you can be able to design the different types of experiments exploiting the ion exchange chromatography. Thank you.